Hey everyone, so my name's Luke. I've been working on the object detection API for KerasCV for about the last year, and I'm really excited to share what we have with you today. I have posted a link to the slides in the chat, but you can find it right up here too. You should be able to just see it on my screen pretty easily. So yeah, this link should work for anyone. But anyways, so first things first, I do want to quickly say that this API is still experimental. We're still finalizing some details as to like some of the parameter names and little quirks here and there and stuff. Object detection is a pretty complicated task, and so there's a lot of ambiguous decisions. So just a heads up, the API is still evolving a little bit, but it should be pretty stable. So a really quick step back to the motivation of why we decided to write an object detection API. So around a year and a half ago, I was not working on KerasCV, and I was working on a few different object detection pipelines. I did that with Keras and TensorFlow, and it was really painful. There was a really difficult I faced many difficult issues in debugging it and in getting the really state-of-the-art results at the time using TensorFlow and Keras. A lot of this has to do with graph execution and stuff like that. But some of the key pain points I faced, I probably spent like 60% of my time making sure that bounding box formats were aligned between various components. When you're looking to assemble a state-of-the-art object detection pipeline, you often have your boxes in different formats, whether it's XY, XY, where each one is represented by a different coordinate, or maybe XY with height, where you have 4 numbers, the top left, and then the width and the height. Or maybe it's like the center width height, where instead of the top left, you have the center. You can imagine how managing this gets really tricky between different projects. And unfortunately, there are actually good technical reasons to use each format at different stages in the pipeline. And so this is really burdensome to end developers. So that was one of the big things I wanted to design the API around. Another one was augmentation. So when you rotate an image, unlike classification, you also have to update the labels. In classification, you don't have to update anything. It's still a picture of a cat. Most likely, you might, if there's a cat, you might crop it out. Probably not, though. But if you crop, even like crop or stretch or distort aspect ratio, anything, you have to adjust your bounding boxes. So this was really annoying. Yeah, in object detection, you often want to be able to perform inference over variable size images. You want agnostic filters to the resolution, or I guess the size within the image of the object. Like even if a bus is shrank down a little bit, it should still be able to detect that bus. Bounding boxes are inherently ragged in that there's a different number between each image. One image might have 100 bounding boxes, one image might have 5. And this is like inherently really hard to represent in like a computation graph, at least in all the modern deep learning frameworks. And then the last one, the difficulty I really faced was metric evaluation. So really the reason I list all of these is basically just to say like object detection is really hard. There's a lot of really, really complicated problems you have to solve along the way. And I hope to show you an API today that I think solves all of these, and I believe it solves them much more elegantly than any other solution that exists today, in a much more modular way and easy to maintain way. So some feature highlights, we have like TPU compatible training loops, which is really great and really difficult to do with bounding boxes because of that inherent raggedness I mentioned, where there's a different number of boxes per image. You can't fit those into a dense tensor because your second dimension, you'll have your batch dimension, and then your second dimension will have a ton of mismatched numbers. You can make this work on TPU by padding with -1s and masking out certain values and the losses and stuff like that. But it's really annoying to do that if you are writing your own object detection pipeline. So we do that internally for you, and it makes it TPU compatible. We have like train time metric evaluation in the computation graph, which is really, really hard to get right. It might not sound that difficult, but this was probably the hardest part of the whole API. Like I think I spent like a couple of months really getting this to work and getting the numerics right on mean average precision, which is a very long to describe metric. I can provide some links to anyone interested in reading about that, but it's very hard to do in a computation graph. Yeah, we have like native support for ragged bounding box inputs, which I'll show off in the demo, and easily composable bounding box augmentations. And I'll also show this off in the demo. Some like API highlights are, we have a very explicit management system for bounding box formats to prevent you from shooting yourself in the foot, so to speak, and giving boxes in the wrong format to the wrong components and stuff. We have a very modular API, which it's kind of hard to show off unless you peel a layer or two back from the models, but it's very modular, and you should be able to use pretty much any component in your own model with no issues. And then we also have native pre-processing and augmentation layers and very readable model implementations. So just to really quickly show off some API like highlights, like why I make such a big deal out of the bounding box formats is like if you have this layer right here, right, like which is a random shear, it shears the image this way or on the y-axis, like it's sort of like rotation, but little mathematically different. And you might wonder, like, what bounding box format should my boxes be in? And in pretty much every object detection project in existence, there's just a either a standard, or you just have to like read the doc string or figure it out, and you have to like visually debug whether or not it's working, usually by plotting your bounding boxes on a few images and showing it with matplotlib or plotly or whatever. So we address this instead by making all of our object detection components support every single bounding box format, and instead you specify which format you use. And this is really nice because as you compose across multiple components, whether it's the augmentation pipeline, the data loading pipeline, or the actual model itself, it becomes like really obvious when you look through and you see, oh, why is this one XY and this one XY with height? It's very obvious that's a bug, and you can very, very quickly run this down and run down these sorts of issues, which I make a big deal out of this because I probably spent 60% of my time on my several object detection workflows I built last year, just debugging bounding box format issues. So this is a really nice API decision that was a little maybe controversial, but I think we're very, very happy with. So yeah, this is consistent across all of our components. And now I'm just going to show off like a few common tasks and jump right into a demo to like not bore you too much with slides. So one, like you can assemble an object detection like augmentation pipeline just like this. Like this is doing a lot of the state-of-the-art augmentation techniques. It's random flip, distorting the aspect ratio, and like this jittered resize layer is actually very well optimized for object detection. You might not realize it, but the way you resize your images in the training loop for an object detection pipeline matters a lot. And then this last one, mix up, actually makes quite a big difference too. And you simply blend the pixel values of two images together. As you can see here, it's like you can't really see what this box is around. That's because the pixels are blended at such a low rate, but the models actually learn to become more sensitive to features by being trained to detect, like, for example, there's still a train in here. It's just the pixels are very much blended out in the background, and this yields to higher scores on your evaluation set, actually, if you do this during training. And so doing this stuff, like all of these, the flipping, the aspect ratio distortion, the jittered resize and mix up, like, historically, this has probably been like 1,000 lines of code to like get all of this right, or it may be a little bit less if you very specifically code it for your project and your input pipeline. But you can do this in like 10 lines of code, which is just like awesome, super, super awesome. So that's one thing. Another thing is, here's how you assemble a model, like a RetinaNet, for example. You just give it a number of classes, a backbone, which can be basically any KerasCV model. We're still working on getting some of the state-of-the-art backbones for the model. You can read more about that in the actual RetinaNet publication if you don't know what that means. And then also we have like some other nice things, like you can provide any set of pre-trained weights that comes with KerasCV. So there's this nice integration between the classification side of the project and the object detection side of the project. And in the near future, we're going to have self-supervised pre-trained weights, which have a much better performance on transfer learning tasks and stuff like that than anything else that we know of right now. yeah, you can do things like only fine tune the feature pyramid network by disabling training for the backbone and all these things. Like there's just like a lot of, basically 99% of users can probably get by just by using our, the notebook I'm going to share at the end of this presentation. But the point I'm trying to make by showing all these different parameters and stuff is we also expose all the little nuts and bolts if you do want to customize your model. Yeah, you can create COCO metrics like this. Very, very easy. In the past, this has been something that's quite painful. Almost everyone uses PyCoco tools to evaluate COCO metrics. Not a very good user experience. It's a package that was written for the COCO challenge, and I think it's like 2011 or something like that, and has not been updated that much since, but most people rely on it to make sure their numerics are identical between, for publication purposes or comparison purposes. So we actually have a very highly accurate set of COCO metrics that work in the computation graph, and they're pretty performant. Spent a lot of time getting that working, and you can just use them like any other Keras metric. And so like when you go to compile your model, same way you do a normal Keras model, just the only difference is you might have multiple losses because there's classification loss and box loss. And yeah, you can give it whatever optimizer you want, whatever list of metrics you want, and it all just works with native Keras APIs. Inference is super easy. You can just save your weights like you would with any model, and you can load your weights like you would with any model and just run predict, and this gives you bounding boxes for those images. So as you might imagine, if you're trying to create an application that actually does this on the fly, you can very, very easily load weights at server startup time and just run predict, or on your mobile device, whatever it might be. So here's some examples. It's just what some predictions might look like. This was not a particularly tuned model, but you can see it's like, yeah, you just run predict and it gives you a general area of where these things might be. And so last but not least, I have a demo in this Colab notebook. I can copy this link over to the chat again, and I'm gonna just open it here though. Cool. So I was actually running fit because I didn't start the training job early enough to have it be done by now, which is totally fine. But the point is the code. But so yeah, this notebook shows off how to do everything that you might want to do with KerasCV's object detection API. So we start off by installing, I have a couple patches that I made for this presentation, because as I mentioned, we're still finalizing some API details. And but yeah, install a couple pip packages, sort out our imports here, and then we actually can remove that. Next, I just show off how to load the data. So here are, we're loading Pascal VOC, which is just a standard object detection data set. It comes in this, TF data format, which is a dictionary with a million different keys. Basically, to make your own object detection workflow work that uses KerasCV, this is basically the only thing you need to reproduce for your own data set. You have to write a function that packages your data into this format where you have images in one key and bounding boxes in another key in a dictionary, and you should be able to copy paste the rest of the notebook from here down and train like a very powerful object detection model. You might want to hyperparameter search a little bit and stuff like that, but the general workflow should be here. Yeah, here we assemble an augmenter, which is just kind of like a sequential model. This will probably be removed before the true release of KerasCV's object detection workflow in favor of a sequential model. But as you can see here, like this is super, super composable. Like right now we have, so I'll go ahead and actually rerun some of these cells so we can start from the top. But so, for example, if we want to remove mix-up and introduce mosaic instead, just so we can see what that looks like, we can just, comment that out and comment it in, which like, this might seem like very intuitive, but that's the whole point, right? Like these historically bounding box augmentations have been very, very hard to compose. And so this is actually pretty great. So we can show this off here. And let's see if it worked with the mosaic. Ah, okay. So okay, funny story. I interrupted the training script and that makes inference mode turn off. So I'll actually need to restart this runtime. Just a quirk I'm still working out that you shouldn't worry about, but it makes the augmentations not apply, basically, is the takeaway there. So yeah, we'll import everything, load the data set again, and this time it should work. While we're waiting for some of this stuff to run, is there any way to take questions while we're here? So yeah, you can see it's mapping to the augmenter here. It's like the graph is all constructed, and now it should have the mosaic of the different images. Oh man, looks like I'm on the wrong branch. So yeah, I guess the mosaic is not quite prepared yet. I thought it was merged in, but I think the pull request to make mosaic work is still not quite merged yet. The point is these layers are very composable. The launch is coming in a couple weeks here, and all these quirks will be sorted out by then. So yeah, we'll just rerun that. You'll be able to see at least the mix-up versions, which are the blended ones. Mosaic is like so you actually, this one's a much better example than the one in the slides. You can see like the faint silhouette of the cat here across this image, and so it actually trains it to detect that as a cat, despite these other bikers in the background. Makes for a much more sensitive detector that detects many more boxes, which is pretty interesting. And then here's the eval set. So yeah, looks about like you'd expect an eval set to. And then, yeah, the last thing we have to do is just construct a model, which we can do right here, and compile it with some metrics like we do here. And yeah, give it any sort of normal Keras callbacks you want. And then you can just call fit like you do with any other Keras model. Because I already ran it before, we can actually go ahead and load the weights so we can get some decent results from what was going on before, or what we had the training job when I started the presentation from. Here are some sample detections. So you can see in here, we're just running model.predict like you would with any Keras model. Like it's just, I guess the beauty of the API is it just very much conforms to the Keras modeling API, which makes it very easy to work with and very easy to reason about. Yeah, the reason this is taking a little while is the first time you run any Keras model, it has to trace the graph of the underlying model, but subsequent runs of this same function would be very quick, like, on the scale of 1/10 of a second, probably less. So should trace pretty soon here. Okay, there we go. So it's done tracing. Cool. So yeah, I mean, this was not done converging or training, but you can see it's starting to learn what the underlying training distribution. It got both of the cows, it got one of the chairs, got the horse in person. Also thought this was a cow, but it's okay. But yeah, it's starting to come along, and this was only like 4 or 5 epochs in, so it'll definitely get there. So we can continue training by running fit. And then the last thing I wanted to show off is you can configure your non-max suppression operation pretty easily too with KerasCV. And you do that by constructing a non-max suppression prediction decoder, which is just a concept we invented, or it's just like a layer, a normal Keras layer basically. And you can give it any sort of parameter you want, like IOU thresholds to prune over, confidence thresholds to prune over, whatever. And so maybe if we run the same thing over the data set we had here, perhaps it will prune out this cow detection or something like that. So Yeah, like it looks like it. Well, it looks like it pruned out more than just this cow detection by increasing the confidence threshold. So, if you want to get optimal scores, usually you have to play with this quite a bit. This non-max suppression operation, you usually have to tune it very aggressively. So, yeah, we could keep playing with this, but yeah, I mean the model's also not converged yet, so it will continue to just get better and better as we allow it to train for more epochs. So yeah, I mean a little short on the presentation, but this is the API, and the beauty of it is that it is pretty easy to show off. It's like it's just native Keras APIs that solve common object detection tasks. And yeah, I mean, you can just run fit like you do with any other Keras model, and it can learn to solve an object detection problem. So we got a lot of nice debugging tools in here too. Like there's a lot of little nuances in object detection, like encoding your ground truth boxes to anchor boxes and training targets. And we expose all that information to you. There's going to be a very extensive tutorial overview of like how to use the API, and that will tell you how to expose and access all the different nuts and bolts. So yeah, I mean, if anyone has any questions, that would be great. But that's the KerasCV object detection API at this moment. It seems a little simple, but there's a lot going on under the surface that I think you'll be very thankful for once you start using the API a little bit, especially when you compare it to other existing solutions. On the front of modularity in particular, I think we do a lot better than anything else out there.